Pull something.
Okay, we've got 1:30. Why don't we get started? Good afternoon, Research Methods. That's pretty good. Welcome to Wednesday of week number 12. We've got some great news. At the end of today's session, we're going to hand out a homework assignment. Let's give it up for yeah, there goes Natalie. All right. So we get a homework assignment at the end of today's session, and I think you'll find that helps us learn even more about complex designs, which is our quest this week. We're on the quest to seek the holy grail of understanding complex designs. So lots to do today. We didn't get yesterday to the video that was arranged for yesterday, so we want to make sure that people are okay with what's going on there. So what I'd like you to do is pop open to the 1112 PowerPoint, if you would please. You can find it either on Blackboard or on the S drive. And I'd like to give you a few minutes to review your notes. I always ask you to take notes on what's going on in the video. And I wonder if you can look over especially slides 1 through 12. We'll start out with that discussion. This is on simple effects. And then we'll use the random number generator and have some folks walk us through some of the slides that we've got. So we'll give you a couple of moments to pull your thoughts together on the first 12 slides, and then we'll make our way on through this. Okay? So this is November 12th, PowerPoint that we're working with, slides 1 through 12. Okay? And I'll call out the random number generator. And we'll do that after we give you a few minutes to think through your notes on this portion. Okay, why don't we draw the line there? Hopefully you've gotten just refreshed a little bit on what you saw in the video, and then we can go on to talk a little bit about this idea of complex designs, and maybe there are 3 different large types of effects or varieties of effects that we can examine. One of them is simple effects, not shown here, but can we just yell out what were the other 2 kinds of effects that we might be examining in a complex design? Main effects and also interaction effects, okay? So we have main effects and we have interaction effects, and then today we're going to be introducing simple effects, which are sometimes, somewhat confusingly, also called simple main effects as contrasted with just ordinary main effects. Okay, so sometimes the terminology is simple main effect or simple effect. And I prefer to call it simple effect because I think it's clearer in terminology. Okay, so we might be looking, for example, at the simple effect of factor A level B1 as one possibility. And then this was something we went into in the video. This is a table that we might ask first about and trying to understand what its dimensionality is. Can we all yell out what the dimensionality is? Okay, it's a 2 by 3 or a 3 by 2, all right? Anybody want to remind us anything about the locus of control? We had some conversation about that in the video. And by the way, thank you for watching the video. I noticed there were something like 34 views, so we got up some good numbers on that. Anybody want to remind us about locus of control? Okay, thank you, Jenna.
It's kind of like the extent to which you believe things that happen to you are determined like externally versus internally.
Okay. Right.
And that you believe that things are done to you.
Okay, right.
Whereas internal is more like taking personal responsibility.
Yeah, right. Okay, so it's an important psychological variable, and lots of psychologists, especially clinicians, might be interested in this variable. I think some personality psychologists are also interested in this variable, and you could use it to apply to just about any kind of measurement that you might have. Maybe you're measuring something like GPA, and you can ask students, first, what is your GPA? But then, why do you think your GPA is the way that it is? And they might begin to give you answers that are relatively externally focused. My GPA is the way that it is because these are the factors that influence that are external to me. Other times you'd have somebody with a more internal focus, and they would say things like, my GPA is the way it is because I make it happen that way. They might even say that whether it's a low or high GPA. They might say, my GPA is low because I haven't been working as hard as I should be, or my GPA is high because it's the case that I've really been working throughout my entire dentistry career and I've made academics my top priority. So it's one of the factors that we're getting at here in this table. Okay, and we know that we have a 3 by 2, and we're looking at the extent to which, or the percentage of responsibility attributed to either uncontrollable circumstances or controllable circumstances here. And then we have these 3 different levels of depression and 2 levels of accident. That's the 3 by 2 that we've had. Okay, so I wonder if somebody could then walk us through the subtraction method here. Would anybody be willing to do that? We've done that. Okay, thank you, Catherine.
So for this one, you would go vertically down, or you could go vertically down. So
Okay.
you could subtract 7 by 30.
Okay.
And you'd get something like negative 20.
Okay, right, and we can just go with integers here, so that's fine. So 7-ish minus 30-ish gives us minus 23. Good, okay.
And 14 and 16, which is 2, and then 16 and 3, which is 13.
Okay, right.
So there is an interaction because there are big differences between all of them.
Excellent, very nicely stated. So we're getting a difference of negative 23 here, negative 2 or thereabouts there, and then something like positive 13. And Catherine correctly noted that we're probably going to have, that's pretty good evidence for an interaction. Strictly speaking, you'd have to run it in SPSS or some other package, but that's pretty strong evidence for an interaction because we have different differences. That's one of our hallmarks for finding interactions. Who's okay with that? All right, really good. All right, that sounds really terrific. Anybody else want to suggest maybe a different way? That was perfect. That would get full credit on a test. A different way for finding an interaction here? Some other way of thinking about this? We could do the subtraction method. That works just fine. Thank you, Jenna. Yeah.
We can look at how the severe symptoms have an upward trend from 7 to 14 to 16 to
Okay.
90.
Yeah.
And non-severe have a downward trend from 30 to 16 to 3.
Yeah.
So then that suggests
Okay, for the people in the back of the room who couldn't see what she just did as she was concluding her statement, Jenna went like this. We're getting a crisscrossing. We have a relatively flat but slightward upward trending severe pattern, and then our non-severe pattern is very steeply coming downward, and that's going to create some kind of a crisscross, very much equivalent to what Catherine offered earlier about the subtraction method. So that's really good. Okay, so we will learn more about ANOVAs next week. That's going to be trying to understand really the numbers behind all of that, but right now we're just focusing on the design issues, understanding that there are main effects, there are interaction effects, there are simple effects, and what we'll do now is, after we've looked at the subtraction method and we saw evidence for an interaction, Jenna gave us another idea about why we'd have an interaction. We can look for 5 different simple effects, and we've got 3 of them here. Okay? And we've actually already gone through some of those. We get some idea about what a t-test might tell us in each of those. We know what the numerator would be, because basically Catherine gave us the numerator when she did the subtraction. The numerator here would be minus 23, minus 2, and positive 13. So we don't know exactly what the denominator would be, but we'd have some differences going on there. So we have 3 of our 5 simple effects, and there is here the simple effect of accident at each level of depression. Okay, so we're looking at severe versus non-severe here, and we're momentarily disregarding this. Okay, these other 2 don't exist just for the moment, and then we'll focus in on this one, and momentarily we disregard those 2, and then finally we focus on that one while disregarding this. I want to make a point about that I didn't make in the video, and that is there is some similarity between main effects and simple effects, and the similarity is as follows. In both cases, we start out with a complex design, and we simplify things. Main effects are a way of simplifying. Simple effects are a way of simplifying. Okay? But the manner in which the simplification occurs is different. In the main effect, we simplify by averaging. Right? So we have to average over levels of one variable. And you might remember that we did that averaging by drawing these mental medians or mental averages, and we were connecting like terms, and we were like adding all the black bars together and finding an average, and then comparing that to our mental average of all the white bars. So we simplified things by getting rid of the other variable, and we did that in main effects by averaging. Here, it's even simpler than that. In the simple effects, again, we simplify things from the complex design, but we simplify by, if you will, disregarding. So here, we're looking at the simple effect of accident, severe versus non-severe, at just one level of this, and we completely throw these away just for the moment. So we don't even average over them. We just disregard them altogether. And probably a first grader can just disregard information, but a first grader might not be able to average. Okay? So averaging is a slightly more complicated process, but it's a way of simplifying the complex design down to fewer dimensions. Who's following that? Okay? So the main effects and the simple effects are ways of simplifying, but they answer slightly different questions. One is based on averages, and one is based on disregarding the other levels of the variable. So here we have 3 of our 5. Okay? All right. And then we have some idea about which one of these might be statistically significant and why. Why don't we yell out which one is most likely to be statistically significant? Real loud? I think I heard it. Non-depressed? Okay, and why is that? Okay, we have all other things being equal, we'd go with the largest difference, and that's probably where we're going to have a difference. Now, we also have a fairly large standard error there, or standard deviation, so it might be up for grabs, but because we've got a really big difference there, we've got a good chance of getting statistical significance there. Not such a good chance here, because we have a difference only of 2, and that's going to be situated in some kind of standard deviation that's quite a bit bigger than the difference score. That might suggest that the denominator of our t statistic here might be even bigger than our numerator would be, and that's going to give us this really puny t value that's going to be centered somewhere in the middle of our t distribution. Who's following that? Work for all? Okay, really good. Okay, so then we can go ahead and we can take a different kind of a slice. We can take this horizontal slice rather than the vertical slice, okay? And we then have these remaining 2 simple effects. We've had 3 simple effects so far, and now we have 2 of these. This one's a little bit different because now in any one of these simple effects we actually have 3 levels. Right? So it's a little bit different than what we had a moment ago. Okay? Which of these simple effects do we think would be statistically significant, and why? Does anybody want to help us with that? Okay, thanks, Kip.
I think the non-severe, because this is just a guess, but the difference between like 30.5 and 3.75 is much greater than between 7 and 6.
Okay, I think that's really good reasoning. Brittany also had a hand up. Same kind of a thing? Okay, yeah.
The decrease, even jumping between non-depressed and slightly depressed, that's a big decrease in what we're...
Yeah, right. Even from here to here is a pretty good jump. Yeah. Okay, so Kip's making the point that this one's a really big jump, and Brittany's saying even that's a pretty good jump. So that I think makes sense to me. Now, one other way to think about this is way back when we were talking about the R statistic. We're not doing an R statistic here, but who remembers talking about the R statistic? It's been a couple of weeks. The R statistic ranges from what to what? Can we yell it out? All right, -1 to +1. There we go. And so if we have an R statistic, and we don't have one here, but you can imagine that if we did have an R statistic that was going to fit this pattern, and this is a roughly circular pattern, can we all draw in the air the best fitting straight line here for this one? Okay, it's going to be flat like that, okay? And so we would have no effect of this variable on that variable on this particular R statistic. Same kind of a thing going on here. Actually, for the severe case, we might get a slight downward trend. If I can cheat a little bit here and give us a little bit of an ellipse that's going downward. Or we might get a slight, I should have drawn that upward, but there's a slight departure from 0. Here in the non-severe case, we're getting a really steep downward trend. Okay, so we probably have a significant effect. If we were to have an R value here, we'd probably have a significant R value. Okay? Who's following that? Okay, and then please go ahead, Katie.
What are the numbers in parentheses next to?
So these are typically some indication of dispersion. And it might be standard deviation or standard error or something like that. Frequently, it's standard deviation. Okay, so it does help us to contextualize that difference. So I think it was Catherine who pointed out, if we did this difference, we'd have a difference of 23, and then we have to put that into some kind of pooled variability. Who remembers that nasty denominator inside of the t-test? We called it thing 1 and thing 2. Remember, it was really, really big, okay? We'd have to put all these numbers together somehow. But that's some indication of dispersion. Okay. All right. All right. So it might be the case, as I think Brittany's correctly pointing out, and Kip's correctly pointing out, that non-severe is going to be significant. So let's say we did a ANOVA on this, okay? And we found out that one of these things was not like the others. At least one of these things is not like the others. What would our next step be, just by way of review? So we wind up with a significant F statistic when we do a one-way analysis of variance on the blue team here. What would our next step be after that? Does anybody recall? Post-hoc tests, okay, right? Post-hoc tests would be our next step. Can we yell out some names of the post-hoc tests for between subject conditions or between subject studies? Tukey, I think I'm hearing, and Chaffee, okay, and Dunnett. So those would help us to pinpoint which exactly are the same. Probably those two are the same. Brittany thinks these two are going to be the same. I think she's probably right. And they might even be, these two are different. These two are probably going to be different. And they're probably going to be different even after we make the correction for post-hoc tests. Right? Even after we make an adjustment, they're probably that different from each other. Okay? All right. All right, so we'd have to run all of that. There we go, Chaffee, Tukey, and Dunnett. Okay? All right. Questions on any of that? Our introduction to simple effects, sometimes called simple main effects. Or comments on any of that? Okay, so far this week we've talked about main effects, we talked about interactions, and interactions are usually the killers. Those are the ones that we spend a lot of time on in this class, and then if you take additional psychology classes, you'll learn more and more about interactions as you go. And then today we're introducing simple effects, sometimes called simple main effects. Let's see if we can put all of that together in this decision tree. And I wonder if somebody can walk us through the decision tree. It's kind of self-explanatory, but some people get lost in this. Anybody want to take us through? Note takers? Okay. All right, well, I'll start us off then. You could imagine that if we had simple effects, we have main effects, and we have interaction effects, we could ask about those in any particular order. We could ask about them in a random order. Usually, most statisticians would say the best way to go is ask the question about the interaction first. Frequently, that's why we got into a complex design. We wanted to know how variables were interacting with one another. So here we have the AB interaction first, and we might ask, is that statistically significant? Now, you and I have learned some tricks for discerning whether that's significant or not. We've used the subtraction method. We've looked for departing non-parallel lines. In the not-too-distant future, we'll be looking at sig values, and whenever something is less than 0.05 in our sig column, we'll say that we can reject the null hypothesis for that. And so in this case, we'll be looking for the interactions first. And let's just say that we don't have a significant interaction. Maybe we come up with similar differences rather than with different differences, and we have relatively parallel lines. Then we can ask about each of the main effects alone. Okay, so we can ask about factor A all by itself. That might be the type of accident. We can ask about factor B all by itself. That might be the level of depression. And it might be that in some cases we have to run an ANOVA because we have more than two conditions. And if that's the case, then we'd have to run some post-hocs as well and make some corrections for cumulative type 1 error and pinpoint where those differences are. If it turns out that we don't have a significant interaction and we don't have any main effects, we can stop. Okay, there's nothing going on in our data set. We ran a test to see if two variables were interacting. We wound up with nothing. Who's okay with that much? That work for us? Okay. All right. Then what we can do is the A by B interaction. If that turns out to be significant, then we might move to the simple effects from that point and see if the simple effects are significant. And if they are, then we'll have to do some post-hoc corrections and again pinpoint where those differences might actually be. But here we're simplifying now by disregarding the other variables in our analysis. Here we've averaged over those. So here main effects we're simplifying by averaging. Here we're disregarding that information. It might turn out that we don't have any simple effects and we can stop. Okay. All right. Who's okay with that? Can anybody remind us why we choose to not look at the main effects if we have an interaction? That's a little bit subtle. So if we do have a significant interaction, and we go this way, we never really make our way back to the main effects. Any notion about that? Mentioned on the video once or twice, but it's a subtle point and might not be obvious. So if we have a significant interaction, why do we become less interested in the main effects? You actually could look at main effects, but we usually don't when we have a significant interaction. Any notion about that? Okay. Sometimes what happens is if you have a significant interaction, you might generate, for example, a significant main effect, but for very uninteresting reasons. And I wonder if I can show you why. Why don't we go to a graph. You don't have to call this up with me. I'm going to see if I can find one from the other day. We'll go to 1111. We get something like this. First, who remembers looking at this graph? Does that look familiar to us? Okay. Can somebody just walk us through, and we'll use our script on this factorial graph? Starts out with, in this graph. Okay, thanks, Meg.
In this graph, the discriminability is plotted as a task with training as the parameter.
Right, okay. In this graph, discriminability is plotted as a function of task with training as the parameter. Okay? Let's take a look at this one. I think when we introduced this way back when, we didn't really ask at that moment if we have an interaction. Why don't we vote with our fingers about whether we have an interaction here? If we think we have an interaction, let's put up one finger to say yes, there's an interaction. 2 to say no. 3 to say I don't know. This graph, do we have an interaction? Okay. What do we think? Okay, some people are putting up a 3. Okay, and that's cool. People are doing a 3. I wonder if we could go with Hannah had a 1 up a moment ago. Do you want to try it?
I mean, just no.
You don't want to try it. Okay. Let's really loud, everybody. What's the dimensionality of this thing? 3 by 2, or equivalently? A 2 by 3. Okay, so that's fine. Few folks. Yeah, Meg, would you try? Yeah, thank you. There's a difference of differences. Wow. Okay, that's a perfectly reasonable way of doing it. Okay, that big thing minus this black thing gives us a big difference. Okay, here the differences are small. Okay, big difference, small differences. Is that? I didn't use any numbers there. I went big and small. Are people okay with that? Okay, so we have differences. We have evidence for that. That's a perfectly reasonable way of doing it. Can somebody think of another way of coming to that conclusion? Okay, thanks, Catherine.
I drew the line.
You drew the line and you just drew it in the air again. Can you draw that one more time for us?
For the white one, it's like
Wow. Okay.
the other one, I don't know.
Okay, right. So it's really steeply coming down here for the white one, and it's pretty flat-ish for the black one. It bumps a little bit, but it's pretty flat-ish. Who's okay with that? A steep slope for the white line and a flattish slope for the black line? Okay. Which is another way of saying big difference, small differences. Okay. So who's comfortable that we've got an interaction going on here? Okay. All right. So that was the interaction. Now I think we're all on board that we've got an interaction going here. We came to this slide because I think it makes a nice example of why you probably wouldn't want to talk about main effects here. I'll ask you about this. Why don't we look at this one? And we'll ask the question, do we think we'd have a main effect of task in this 3 by 2 design? So we've already asked about the interaction. Now we'll ask about the main effect of task. And we'll let you think it through, do your mental gymnastics. Vote, yes, I think there's a significant main effect of task. Or no, I think there isn't a significant main effect of task. Or 3 fingers for I'm not sure. Okay, some people are being very, very honest. Very good. I think I saw a quick response from Kip, and I think Kip's got the correct number. He's putting up 1, and I think there probably is a significant main effect. What's your reasoning here, Kip?
If you take like the average
Uh-huh.
direction and speed, it's
Okay.
higher like bars.
Right, okay. So we're going to average because we're taking main effects. Here we're going to collect like terms on the task variable. Here we have 2 directions, okay, right, 2 direction bars. And for those of you who couldn't see it, he was gesticulating in a way that this was going to be quite a bit higher than either of the other 2. Who's okay with that? We get a greater mean in direction than we do in speed and than we do in luminance, okay? So this average is quite a bit higher than the others. We probably have a main effect. First, who's okay with that? And they see where that came from. Did I lose anybody there? Okay? All right, so that's a really good way of thinking about it. We have an interaction. It appears to be the case that we have a main effective task. Now we'll see if we can, with that in our back pocket, we'll see if we can come to the answer to the question, why do we go with interactions first? Interactions make it difficult to interpret main effects. You can actually run them, and you can do what Kip just did, and he correctly came to the conclusion that you probably would have a significant effective task. The problem with that is we would conclude that direction has a higher mean than either speed or luminance. And that actually is true. It does have a higher mean. But the statement that direction has a higher mean than speed or luminance is a little bit misleading here because that's emphatically not true before direction training. Right? If you look at before direction training, we only, those are pretty similar to each other. The black bars are pretty similar. After training, the white bar shoots up in the direction case, but not over here. So it's a little bit misleading maybe to say that direction is going to have a higher discriminability than the other 2. It actually does, but it does on average only because the average gets drawn up by the after direction training component. Okay? So strictly speaking, he did exactly the right thing. He computed that, but it's a little bit misleading because it would suggest that direction will always be higher, but it really isn't. It's only conditionally higher. In fact, this is a great example of an interaction. Okay? Direction is higher, but if and only if we're after direction training. Okay? So you can imagine that this half of the room happened to have run maybe the test before direction training, and they would have gotten the black bars, and they would see no difference. That half of the room maybe ran the test after direction training, and they'd see this huge difference. Both of these folks would show up at a conference, and some of you would say that the task doesn't matter at all. Others would say task matters a whole lot. Which group is right? Well, it depends. Okay? So it's a little bit difficult to say that there's an effective task when it's so contingent on the training here, even though, strictly speaking, the average works out that way. Who's following that? Does that work for us? Okay. So you've heard about the statistician who says that he's got 1 foot in boiling water and 1 foot in dry ice, and on average he's very comfortable. Okay, right? We can take these averages, but they might be very misrepresentative of what's going on out there in the real world. Okay. All right, so we came back to this because of one of the items in today's PowerPoint, by which I mean the 1112 PowerPoint. We're trying to understand our motivation for making that the first question in our decision tree. Okay? All right, really good. Questions or comments on any of that? Okay, why don't we do this? Why don't we have an extra credit opportunity today? Okay, so what we'll do is we'll give you the chance to make some extra credit. And if you'll put away your all of your stuff, all of your notes, take out a blank sheet of paper. And if you don't respond well on this one, you don't lose any points. This is not a pop quiz. This is an extra credit opportunity. So this should always be good news whenever we have an extra credit opportunity. Slater box number up top, please. All notes away. Okay. And what we'll do is we'll use one of the extra credit questions, actually one of the pop quiz questions, but we'll treat it as if it's a extra credit question. Why don't we take question number 3? I think it's a good one. Really requires a lot of thought. So question number 3 is, in your own words, explain how researchers could use complex designs to test a theory of why natural groups differ. And the way I'd like you to answer this is you don't need to give an example, just give us some bullet items. Give us some bullet items, and we don't need sentences, we don't need paragraphs, just some bullet items on how researchers could use complex designs to test a theory of why natural groups differ. Just bullet items, and when you're done, we'll put them on the back table. Bullet items only would be fine. We don't need paragraphs. We don't need an example. Just bullet items will do the trick. Thank you, Katie. All right, the answers are coming in. Wow. Good extra credit opportunity. Okay, I think they're just about all in. Anybody else? Ah, here's Meg. Okay. All right, thank you. Thanks very much. All right, I have to go back and check. I think this might be something like our 6th extra credit opportunity. I'm pretty sure we've had more extra credit opportunities than we've had pop quizzes. So we can move that around if you want. We can have more pop quizzes. No? No, people are, okay. All right, really good. So we'll come back to that in just a second. We'll see how people did on that one. Why don't we start out with the top issue. What is the simplest possible complex design? Can we all yell it out? All right, that one would have been easy, right? Okay. In your own words, explain what is meant by the phrase natural groups. Can anybody help us out with that? We'll go with Katie, and then we'll go to someone else.
It's when you're looking at groups with pre-existing conditions, so like age, gender, like things you can't assign to someone that
Right.
they already acquired.
Yeah, you know, I've been teaching this course for 13 years, and only in the last 2 years has the phrase pre-existing condition come to mean something in the popular vernacular, right? That is, if you've been following the healthcare debate, there was a issue there about whether when you're getting healthcare, can you disregard a pre-existing condition. What they meant by that was a medical condition. What we mean is any kind of a trait that is not being assigned. So gender is a good one, age is another one. Lots of pre-existing conditions that we're very interested in. And so sometimes groups form naturally. We don't need random number generation in order to get there. So sometimes we're going to be looking at natural groups in our complex designs. Okay. In your own words, can somebody explain how researchers could use complex designs to test a theory of why natural groups differ? So this was the extra credit bit. We're looking for some bullet items here. Anybody want to shout out some bullet items? Natalie's got something.
Develop a theory.
Develop a theory, okay? So we're going to develop a theory about why the groups differ from each other, okay?
Identify variables to manipulate.
Okay, very critically, right? Yeah, we're gonna. So the natural groups are not something that we're manipulating directly. They come to us from nature. Okay, but now step 2 is to develop a variable that we can manipulate, and that's an idea about an experiment. And by the way, in the homework assignment later that I'll pass out, I will ask you to design 2 experiments of your own, and we are looking for something that's manipulated there in the experiment. Okay, so that's really great. We've got a theory, and then we've got something to manipulate. Can you say just a little bit more about what to manipulate?
So like you said, something that's not the natural.
Okay, so it's not going to be natural. We're going to be manipulating, and hopefully we're picking a variable that we can manipulate that's relevant to our theory. Okay, and then what's our last bit, Natalie? Do you want to finish that?
Test the interaction.
All right, test the interaction. How many people got all of those? Yeah, some of us? Some of us got all of those? Or okay, I know, test the interaction. All right, that's going to be the third part. Those are the 3 bullets, and those are actually spelled out in our readings. Please go ahead.
Yeah, I remember that from the video, but how does that explain like why natural groups?
Good. Why don't we do a... Right. So why don't we go through an example trying to understand how those 3 steps alone could work in the example that we're about to give, but they could actually work in almost any kind of study where you're trying to understand why natural groups differ. So this, I think it's a very powerful set of 3 steps, and we're going to see one example that we might have. Just in case you're interested in what went on in the video, we're not going to watch the video now, but here's the chance for me to put this up. There's me, and there are the 3 steps, okay? Okay, and this is at something like the 21-ish, 22-ish minute mark, something like that, okay? Develop a theory, identify a variable to manipulate, and test the interaction, okay? And then you might begin to see what particular example was given there, and this is one of the ones that's developed in the book. And so hopefully we can get this to answer Kip's question. How do these come together to really tell us about this? Anybody want to start us out? Maybe that's a little reminder about musicians. Give you that much. Can somebody begin to explain how that works? Okay, why don't we go with Meg, and then we'll have Jenna go from there too.
I think you were talking about how they developed, they have a theory that musicians have a better, better memorize a musical phrase.
Okay, a melody, yeah, okay. Right.
Than non-musicians.
Okay, but if I can pause right there. So let's say that we do a test, and we're doing a recall test. Maybe we're cognitive psychologists, and we find out that we want to know recall for different kinds of things. In this case, we want to know recall for melodies that people might have heard. And for whatever reason, we're comparing musicians to non-musicians, or maybe we're just looking at the data set in general, and we happen to see a pattern. Maybe we know these folks and we know something about them, and we notice that the musicians are doing better than the non-musicians on recalling melodies. Okay, so that's the first phenomena that we have, and those are natural groups, right? So getting back to Kip's question, we don't assign people to be musicians or non-musicians, at least not typically. What we have instead is people come into our study having played an instrument maybe for many years or not having played an instrument for many years. Okay, so who's okay with the idea that musicians versus non-musicians, typically that's a natural group. We're not assigning people there. And then in this hypothetical that Meg is developing for us, there is maybe a difference in their capacity to recall melodies. Okay? All right, so I interrupted you. Do you want to go on to, that was a really good start. Do you,
I was a little bit confused with the good or poor stuff.
okay, all right, why don't we try that? I wonder if Jenna would like to pick up on, okay, thanks Jenna.
Well, it was my understanding that the structure was based on the good versus poor structure was of the melody.
Uh-huh.
So a good structure would be a melody that really follows kind of what you learn in music theory.
Okay, okay.
So it's something that is recognizable,
Mhm.
you understand the form.
Yeah.
And poor structure would be something that's not so easily recognized within the form of music theory.
Yeah, right, okay. So many of us probably haven't taken music theory, and you shouldn't feel like you have to take music theory to understand this pattern. But if you're a trained musician, you go through courses in music theory, and you learn about how melodies are constructed, and you learn lots of different patterns and so forth, and they help you to organize information. When we're organizing information, sometimes a word that we use in psychology for that is chunking. Who remembers chunking from Intro to Psych? Anybody remember the chunking phenomena? So all of a sudden now you can take in lots more information if you can organize it according to chunks. So if you now have taken music theory lessons, then one idea is that maybe you're recalling melodies better because you can somehow chunk this part of the melody, chunk that part of the melody, and now you can recall the whole thing because you're really good at chunking because that's what you learned in music theory. Who's following that? Okay, so maybe that's one theory. I wonder if anybody can develop two other possible theories. I mentioned them in the video. It could be that they're using chunking, but there might be other explanations for why musicians are doing better than non-musicians. Yeah, Catherine, thank you.
I think one you mentioned was that people with better memory are just drawn to music in general.
Yeah, it could have been, right? I'm not saying that, that's at least a possibility. So we might have something like this. It's our favorite bell curve. Okay, and this is something like memory ability. And this is higher memory ability, lower memory ability. This is probability, as always. And it could have been that for whatever reason, people who are drawn to music happen to come from this half of the distribution. Okay? And that might explain why it is that these folks are doing better when you ask them to recall melodies. Of course, that would also predict they do well in recalling anything, right? Not just melodies. Okay? That's a perfectly reasonable alternative explanation, which in fact is falsifiable too. Okay? Is there another one? So they could just have naturally better memories. One other variation? Yeah, keep going. Thank you.
Maybe somehow music increases your memory.
Yeah, your music increases memory, or music training might increase memory in general, not just for particular melodies. So it could be that the music makes you a better memorizer. It could be that you were a good memorizer to start with, and that drew you to music. It could be that you've got something very specific here, the idea about the chunking and music theory. Okay, so at least three different theories going on there to explain why it is that these folks are doing better. Who's with us so far? Okay, so now we've developed actually a series of theories, and now we need something to manipulate. Okay, and I think it was Jenna who correctly described for us that some melodies adhere to what we learned in music theory class. We'll call those melodies with good structure, and then some melodies have relatively poor structure. Okay? And it might be the case that if we give musicians melodies that have poor structure, they can't use any other chunking rules on it. They don't apply here. So then they're going to be hosed. Okay? Now, all of a sudden they're going to be back to normal levels because they can't use their usual bag of tricks. They can't chunk these. Who's following that? Okay? So that's our manipulated variable. Right? We have that under experimental control. We can control the stimulus usually, and we can have stimuli that match music theory very beautifully and stimuli that depart radically from this. So these would be good and poor melodic structures. Okay? And then what we can see, hopefully that's viewable for all of you, we're measuring memory ability for musicians and non-musicians. So training is our variable, it's our natural groups variable, and we're asking how well those are recalled if we have good versus poor melodic structure. And the musicians are doing really, really well on those melodies that have very fine melodic structure in accordance with music theory, and they're doing really quite poorly if the melodic structure doesn't adhere to music theory. So this actually falsifies a couple of things. They really don't have better memory in general. Music itself didn't overall increase memory ability. It only gave you the capacity, maybe this training gave you the capacity to chunk. And you can chunk only when chunking is appropriate. Good melodic structure. The non-musicians do equally poorly in those two cases. Who's following that? Okay, so you can see that we now have an interaction. So we're going to test for the interaction. The interaction is there. And the interaction would say that we get a big difference in this case and a small difference in that case, where we have non-interacting or non-parallel lines. And so this is entirely consistent with our theory that, in fact, the reason why musicians are better is because they are using music theory to make that distinction. Okay? Please go ahead, Jen.
So on that chart that we were looking at before, so we would say, yes, there is an interaction, and then because there's an interaction, we would go down to looking at the symbol.
Right, and one simple effect is, what kind of a difference do we get here? Right? Because we're not really out of the woods yet. We do need to have an interaction, right? Okay. And then what we need to see is the interaction is also in the predicted direction. The musicians are doing better only selectively, and the non-musicians are relatively insensitive to that manipulation. So you follow that chart just right.
Use the subtraction method rather than averaging to determine this.
Yeah, once you're at the point of looking at simple effects, okay. In this particular case, we can draw that circle there and that circle there, and subtraction would work quite well. Yeah. Okay. Who's following that? One more example. It's a related kind of example. One of our professors here is Dr. Frank Hassebrock, and he's a cognitive psychologist. He has many different expertise. He looks at cognition as we age. He also looks at this phenomena of expertise itself. So what is it that makes somebody an expert? I've got a really fun article that I'd like to share with you. Maybe next week. I think you'll get a really big kick out of it. But one of his claims is that, and what other people have shown too, is that you can use these kinds of steps to show why natural groups differ. And there's one that you might remember from Intro to Psych on chess masters. Does anybody remember hearing about chunking and the people who are really, really good at playing chess? That's a frequently used example in Psych 100. Anybody recall an example like that? Well, the idea is something like this. What you can do is have these two folks, will have Hannah and Maren playing chess on each other, and they play for about 10 minutes straight. And we'll pretend that they both know about chess and they're playing to the best of their ability. Okay? And now a few pieces have been taken from each of the sides. We stop the play, we bring in a chess master, and we let the chess master look at the board for like 5 seconds. And then the chess master has to look away and try to recall the position of all those pieces that remain. And the chess master nails it just like that. Okay? They have no trouble memorizing that, which I think is really interesting. Is anybody here a chess master? How many chess novices do we, or chess sort of non-masters do we have here? Mostly non-masters, okay, right? The chess master can grab that immediately. Now, this is what's interesting. Let's say that there are 15 pieces on that particular board. You can take the same 15 pieces, take out a random number generator, and scramble them randomly, okay? Now you bring the chess master back in. Chess master, look at the game that, wink, wink, these two just played, and they're randomly positioned. Chess master is clueless. Can't position those same 15 pieces. 15 pieces in either case, but can do it really well if it was played in accordance with the rules and can't have any recall of this beyond what a novice could do if they're played randomly. Who's following that? Okay? So again, the idea is the chess master is probably looking at that and very quickly discerning that knight is about to take that rook or something like this, and they know where all the action is, and they get it just like that. Really, really cool. Really cool. Okay, so another example of expertise that might be elucidated by something like this. Okay. All right, questions on any of that? why don't we go ahead then and just finish off the idea about hypotheses. That was the next section in our 11-12 PowerPoint. Okay, so we made it through section 1. Section 2 is quite a bit shorter. It's got the hypotheses, and many of these are straightforward. We start out with in the population. We know that we're comparing means in most of these designs, so we can just look at the mean effect for factor A, and we could say all levels of factor A are the same. We can do the same thing for factor B. And then for the interaction, we might say something like this. In the population, differences among the levels of factor A, so we're talking about the subtraction method there, will be the same at each level of factor B. Right? That would be a null hypothesis for the interaction. So instead of having different differences, the null hypothesis is calling for very similar differences, okay? Which would suggest that we don't have an interaction. Who's following that? Okay. Anybody lost by that? Yeah, okay, so here we are. We're talking about the null hypothesis for the interaction, okay? And are we okay if we just think for a moment back on the subtraction method that we're looking for different differences, okay? And when we find different differences, we have evidence for an interaction. If we find similar differences, we have no evidence for an interaction, okay? And this statement is basically saying that, okay? It's basically saying that differences among the levels of factor A will be the same at each level of factor B. So we take the first difference, that might give us a 0. Second difference might give us a 0 again, a 0 and a 0, same, okay? All right. Okay, so that's all very generic. We've got here factor A's and factor B's and so forth. We can just plug in some actual variables that might be of interest. And so we'll put in, for what used to be factor A, this idea about violations of physical laws. And we might ask about the plausibility of a story. And we might be systematically manipulating how many physical violations were going on. Maybe we're suspending gravity, maybe we're engaging in time travel, maybe we're changing the ways in which light or sound operates. We can fool around in our story with what's going on physically, and we can have 0, 1, 2, or 3 violations, and then participants rate the plausibility of that story. Okay? All right, and then the researchers investigate whether the plausibility ratings depend on the number of violations, as we did a moment ago, and also the extent to which the participant happens to be manic. This might be a clinical variable. Who remembers hearing about mania, the flip side of the bipolar disorder? Right? So there are moments of depression, there are moments of mania. We might ask, gee, is that a predictor also, or is that an important variable? So now we have 2 factors, A and B, and we can look at the A by B interaction. Right? So we can look at factor A all by itself, number of violations, factor B, which is this mania, and then we can also look at differences among the number of violations will be the same at each level of mania. So now we've just plugged in the actual variables, but again, the idea is we're looking for either different differences or same differences, and for the null hypothesis on the interaction, it would predict same differences, that we don't have an interaction. Who's following that? Okay. One last one, and we'll call it a day. We can now bump it up a notch and go to the 3-way interaction. Okay, so this is still a complex design, but it's now gotten more complicated because now we've introduced even a 3rd variable, which we'll call generically C. Okay, right? And it might look something like this. In the population, the interaction between number of violations and mania, that was the 2-way interaction that we had a moment ago, that will be the same at each level of gender. Okay, so we have a male level, we have a female level of our gender variable. And maybe we're going to get an interaction at one of those and that same interaction at the other. Or maybe we get very different interactions. And this is how we would specify the 3-way interaction. Okay? Now we're looking at factors A, B, and C. Okay? So things get pretty complicated quickly. And we're only at 3 variables. Right? The real world is going to have tens or hundreds of variables or more than that. But this would be a little peek into how you would start to explore the very complicated real world using complex designs. Questions or comments on any of that? Okay, real good, real good. So what I'll do now is I'll hand out the homework assignment. And in the homework assignment, we're going to ask you to do a little bit of graphing. We're also going to ask you to harken back to simpler designs when we just had one-way ANOVAs, and one was a one-way within, one is a one-way between, and you'll have the opportunity to create some experiments. Please, experiments have manipulated variables. Please make sure that you make note of that. If you'll take one and pass, and if you have any extras, please pass those on back. Will somebody see Sasha?
Yeah.
Okay.
Another one.
Okay, can we hand one over there? And do we have an extra? I think think there were 4 sets of 4. I think I've got one more up here for Sasha. Is there an extra somewhere? No? Okay. Here's one for Sasha, if you would. Okay, thanks very much, and I look forward to seeing you on Friday. Thank you, Maureen. Thank you.